Assalamu alaikum everyone. Today me and my group members will be solving a very interesting riddle, the Monty Hall problem. This riddle was made by an American statistician, Steve Sullivan in 1975. We'll see how Bayes' rule will help us in solving this question. The Monty Hall problem. Suppose you are invited in a game show and you have three doors in front of you. You are told one of the three doors has a car behind it and the remaining two have a code. You are asked to choose one of the doors in which you think that there's a car. And the game show host, Monty Hall, who knows what is behind the doors, has to open one of the two remaining doors, and the doors he opens must have a code behind it. Given that you choose to open door 1, now Monty has to open door 2 or door 3 to reveal a code. Monty opens door number 3, which has a code. Then he asks you a very simple question, that do you want to switch to door number 2? Now, the question that pops up in your mind is that should you really switch? To solve, to answer your question, we'll define events. Event number W, which is that there's a car behind door 1 that was your initial choice, and without switching, you win the game. And the event E, that there's a code behind door 3 that the Monty opened. What we really need to find over here is the probability. The probability of the car being behind door 1 that you initially chose, given that the door 3 that Monty opened has a code. To solve this through Bayes' theorem,
Now, using Bayes' rule, we can express our desired probability as the product of the likelihood probability, that is the probability of E given W, and the prior probability, that is the probability of W, which is then normalized over the probability of event E. We can expand the denominator using the total probability theorem like this. Now let's define our individual probabilities. The probability of W, that is you win if you don't switch, is the probability of a car behind door 1. So there are three doors and one car, so this probability is essentially equal to 1 over 3. The probability of losing with no switch is equal to 1 minus the probability of winning with no switch, which equals 2 over 3. Now, the probability that Monty opens the door with code, given there's a car behind door 1, and the probability that Monty opens the door with the code, given there is a code behind door 1, are both equal to 1. Because no matter if there is a car behind door 1 or not, Monty always opens the door with a code. Putting the values we just figured into the Bayes rule formula, we obtain that the desired probability W given E is equal to 1 over 3. Now, what can we infer from our solution or final probability W given E? Probability of winning without switching is 1 over 3. So if you switch, the probability of winning is equal to 1 minus 1 over 3 equals 2 over 3. So from this example, we can see that if we switch, we have a higher probability of winning, about twice the chance of winning than we had if we don't switch. Now let's look at a special case of the Monty Hall game. Previously, we assumed that Monty is unbiased when opening the doors. But you are a big fan of the show and have watched it multiple times. You notice that upon choosing gate 1, Monty opens door number 2 20% of the time and door number 3 80% of the time. Given Monty opens door 3, should you switch or not? Let's first define our events. C of I is the event that car is behind door number I. So C1 is the event that car is behind door 1. D2 is the event that Monty opens door 2 to show the code, and D3 is the event that Monty opens door 3 to show the code. W is the event that you win if you switch. What we want, we need to find the probability of winning with switching strategy given Monty opens door number 3, which is the same as the probability of car behind door 2 given Monty shows a code behind door 3. So you switch to door 2 and win the car. Using Bayes rule, we can define a desired probability as the product of the likelihood, that is the probability of D3 given C2, and the prior probability, that is the probability of C2, which is then normalized over the probability of D3. The denominator can be further expanded using the total probability theorem. Now let's investigate what each of these probabilities are and their values. Since there is one car and three doors, the probability of there being a car behind each door is 1 over 3. P probability of D3 given C1 is the probability that Monty opens door 3 given car is behind door 1, which as stated in the problem statement is 80% of the time, as he prefers opening door 3. Probability that Monty opens door 3 if car is behind door 2 is 1, essentially because Monty has to open the door that has a goat, not the car. So if door 2 has a car, he has to open door number 3. The probability that Monty opens door 3 if car is behind door 3 is 0, because Monty cannot open the door that has the car, as this will defeat the purpose of Monty's game. We substitute all these values in our formula to get the probability C2 given D3, which we find to be equal to 0.556. Now, what's the conclusion we can draw from this? That if you switch, you have a slightly better chance, around 5.6% more chance of winning compared to if you don't switch. However, we observe that the probability of winning on switching has decreased compared to the normal case where Monty was unbiased. So that's all from us. Thank you for watching.